Assalamu alaikum. Today we discuss about this mechanical problem. Actually, this problem is related to the fluid mechanics, and gradually we'll discuss this type of problem step by step. At first, we'll discuss theory and then formula, and then we try to solve according to formula solution or problem. Okay, let's start. This one is Newton's law of viscosity. What is the called Newton's law of viscosity? And this, if we consider, don't consider the number, just to consider this is the profile. This is the viscosity profile. Just you consider, and this here some is gradient line. Is at first we have to know the what is the called the gradient line. Here, if you consider this one is the this create the is like a triangle. If we consider that this is gradually increase the obstacle or resistance or shear stress, what can we say, but it is called the gradient. It is called gradient. We'll express that as the gradient equal to and du divided by dy, and another is the shear stress. This is the shear stress. Shear stress we denote by tau. Okay, this one is the y and there is the u, this x-axis. The what is called the Newton's law? Newton's law formula we know the is proportional to du divided by dy, the gradient we know, or we can say this equal is tau is equal to is the shear is the dynamic viscosity du divided by dy. Here this one, what is this one is the actually we know that this one is the and wait for sometimes. This one is the viscosity. This was the viscosity, and du divided by dy. This one is the velocity gradient, or we can say the rate of shear formation. Shear formation. Okay, and here one thing, this one is very there. Here is the very crucial shear formation. Here is the wall. If you consider this is the wall, here is this layer is the here velocity is 0. Here velocity is 0, but in gradually increase the velocity, and that is velocity. We can say the total resistance, F equal to in pipe, for pipe, F equal to pi dl. Okay, I think it's clear too. This is the Newton viscosity formula, and that theory actually the shear stress between the adjacent layer. This is the two layer adjacent layer directly proportional to the gradient. Declination to the gradient. Shear stress is directly proportional to the gradient line, but here between the two adjacent layer. These are two adjacent, one layer and two layer. I think clear to you. And now we'll go for solution of problem. Here we can say for a plate flow over the horizontal plate, and velocity distribution is given also u equal this, and u equal to y minus 2 y square, and where velocity is in meter per second and distance y meter, and above the plate. Shear stress at the distance also given, and absolute viscosity fluid equal to, if the air will be the 0.9. okay, and now we know we have to find out the new viscosity. We have to find out the absolute viscosity is given, and distance. Horizontal plate viscosity distribution is given, and we have to find out the shear stress. The shear stress at the distance. Okay, shear stress equal to, we know this one is mu equal to d divided by dy. Here velocity gradient we don't know, but we know this equation, and we'll derivative with respect to dy. If we do 1 minus 2 into 2y, that means 1 minus 4y, and here we'll put, we know y equal to 0.2 meter has given, then du divided by dy, we know 1 minus 4 into 0.2, then we'll get 0.2 per second. Okay, and then we just we put the whole, because we know here is a point is given, is the absolute velocity has given. Absolute velocity is the mu. They have just put the below 0.9 into 0.2, and we'll get 0.18 Newton per meter square. Okay, answer. And next one is the next problem is the rectangle plate. This is the rectangle plate. This one, the rectangle plate. Weight is given, and actually here we'll solve the 100. Okay, 100 Newton. If this weight is the 100 Newton, and having the dimension, this because it's the dimension, then A equal to, we know, L into width. That means L equal to width is area, and also sliding angle has given, this 30 degree has given, and there is a film having thickness of 1.2 millimeter between two surface. Between the surface their thickness is given 1.2 millimeter, and if the velocity of plate is fluid, dynamic viscosity is also given, Dynamic viscosity, we know the dynamic viscosity. Dynamic viscosity has given dynamic viscosity, and then we know the formula: stress equal to shear stress equal to mu du divided by dy. Here stress equal to, we know the F by A, and equal to d by dy, and F is given. F is the and 100. F actually, F equal to, we this one is not a real condition because it's 100, but F equal to force is acting over the this way. So we know F equal to weight sine 30 degree, then 100 sine 30 degree equal to 50 Newton. Okay, then F equal to, know F 50 divided by area. What will be the area? Area is the also distance. Okay, the area 0.86, the multiply by L length. What is the length? Is the 0.85 into 0.9. Then after multiplying, we'll get the 0.86. Approximately, and then okay, is the 0.86 or 0.86776. Okay, it will be the 0.76 meter square. Okay, .76. Mu also is a direct viscosity we have to find out, and U equal to, we know U equal to the 0.35 is given, and then is the dy equal to initial. That means if final minus initial, and final is the point 1.2 minus 0. That means 1.2 inverse 10 inverse 3. 1.2 inverse 10 inverse 3. Then we'll get this answer. Then we'll get our desired value, and our desired value will be 50 into 1.2 into 10 inverse 3, and 0.67 into 0.35. Then we get the 0.22 the Newton second per meter square. Okay, and both two example is the same, is both are homework. If you understand before two solution, I think these three is you can able to solve this three problem. Thank you. You should try. If you don't get this proper solution, I will give in the solution in another here. Okay, don't worry, but you have to try. But you have to try.